What lies beyond the horizon of our visible world? Is this vast space full of unexplored worlds and galaxies unlike any other? Could it be the location of parallel universes and new dimensions? Perhaps the origin of mysterious planetary events is not yet understood? Join us on a journey to the edge of the world as we explore these questions and uncover the mysteries lurking at the edge of the universe. The universe is a vast and ever-expanding apparatus of space, time, matter, and energy. This includes everything from the smallest subatomic particles to massive clusters of galaxies spanning tens of billions of light-years. Since the Big Bang, which occurred about 13.8 billion years ago, the universe has continued to expand and separate galaxies at speeds that may exceed the speed of light. The phenomenon is attributed to a mysterious force called dark energy, which accounts for 70% of the total energy density of the universe. Along with the dark, which makes up 27%, these invisible elements have a significant impact on the creation and evolution of the world. The very fabric of the universe is woven of galaxies, which are magnificent islands of stars, planets, black holes, and nebulae. Our own Milky Way galaxy, for example, is a complex spiral of over 100 billion stars, each potentially containing planetary systems. Gravitational forces carefully perform this cosmic dance, pulling stars into orbits around galactic centers and linking galaxies into huge clusters. However, amidst this grand order, the universe is also a realm of incredible violence and change, where stars explode in supernovas, black holes devour matter into nothingness, and cosmic rays hurtle through the void at nearly the speed of light. This delicate balance of creation and destruction governs the cosmos, painting a dynamic picture of nature at its most extreme and majestic. Scientists approach the concept of the edge of the universe not by envisioning a physical boundary that can be encountered, but rather by considering the limits of our observational capabilities. The observable universe is defined by the distance traveled by light since the Big Bang, and spans approximately 93 billion light-years in diameter. This represents a cosmic horizon, beyond which we cannot see, because light from those regions has not yet had time to reach us, due to the finite speed of light and the constant expansion of the universe. This edge, known as the observable universe, is constantly expanding as light from new objects finally reaches us after billions of years of travel. Cosmologists use a variety of techniques to look even deeper into the vastness of the universe. Instruments such as the Hubble Space Telescope and the soon-to-be-launched James Webb Space Telescope capture light from distant stars and galaxies, giving us snapshots of the universe as it was billions of years ago. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, help delineate the boundaries of the observable region, displaying the oldest light we can detect. However, these instruments only reveal to us that part of the vast universe that is within our current window of observation. Beyond this edge is the unobservable universe, which is still shrouded in mystery due to its remoteness even from the fast speed of light. The edge of the universe is therefore best understood not as an endpoint, but as the horizon of the knowable cosmos, forcing ever deeper questions about what might exist beyond it. The observable universe is essentially everything we can see or detect from Earth. Bounded by the finite speed of light, which is about 300,000 kilometers per second, we can only observe objects whose light has had time to reach us since the Big Bang, which occurred about 13.8 billion years ago. This is a spherical slice of space centered around our vantage point and spanning approximately 93 billion light-years in diameter. Within the observable universe, we encounter a variety of cosmic phenomena. Galaxies such as our Milky Way are scattered like islands in this vast ocean of space, each containing billions to trillions of stars, as well as many planets, nebulae, and black holes. When we look farther out, we also see quasars and the cosmic microwave background radiation, which is the afterglow of the Big Bang and represents a kind of fossil record of the universe's infancy. Observing these distant objects helps us not only to map the structure of the universe, but also to understand how it has evolved over billions of years. The observable universe is an ever-expanding frontier, revealing more and more information about the beyond and the fundamental nature of the cosmos itself. The observable universe is astonishingly large. Its diameter is about 93 billion light-years. This means that if we could travel at the speed of light, which, by the way, is an unfathomable 300,000 kilometers per second, it would take us 93 billion years to get from one edge of the observable universe to the other. This colossal sphere spans billions of galaxies, each inhabited by millions and trillions of stars, and even more planets. Despite such vast distances, it is important to note that the observable universe is only what we can currently observe. In fact, the universe may be much larger, potentially infinite, making our observational boundaries only a small window into a much grander cosmic tapestry. The enormity of the observable universe is also reflected in its scale relative to familiar objects. For example, the Milky Way galaxy, which itself is massive at about 100,000 light-years in diameter, is only a tiny dot in this vast expanse of space. Even huge galaxy clusters, such as the Virgo supercluster that contains the Milky Way, become mere specks within the observable universe. The cosmic microwave background, CMB, the oldest light source detected, adds to our understanding by displaying the universe as it existed some 380,000 years after the Big Bang, further emphasizing the immensity and age of the observable sphere. It is an awe-inspiring reminder of how vast and ancient our universe is, and how our understanding of it continues to evolve with each technological and scientific advancement. Current theories about the size of the universe revolve around two main options. The universe is finite but has no boundaries, or it is infinite. When cosmologists speculate about a finite but limitless universe, they often use analogies such as the surface of a sphere. Just as the surface of a sphere is a finite two-dimensional region with no edges, the universe can be a three-dimensional space that loops back on itself, meaning you can theoretically travel in a straight line and eventually return to your starting point. This idea is consistent with the rules of the general theory of relativity, Einstein's groundbreaking theory that describes gravity in the fabric of space-time. However, this does not mean that the universe is small. Even if it is finite, it can be unimaginably large. On the other hand, the concept of an infinite universe assumes that space extends without end in all directions. This assumption is consistent with observations and mathematical models showing that the overall shape of the universe is flat on large scales. A flat universe with no curvature suggests that space could extend to infinity. The idea is supported by measurements of the microwave background radiation that scientists study to understand the conditions of the early universe. These measurements show that the observable universe is very homogeneous and isotropic, and that if it were flat, it would probably be expanding. Both concepts offer exciting ideas, but they are also complex and mysterious. An infinite universe but raises questions about the topology and geometry of space. An infinite universe challenges our understanding of infinity. Moreover, the true size of the universe remains elusive because our observations are inevitably limited to the observable universe, leaving what lies beyond, be it additional galaxies, different physical laws, or even other universes, to theorists and future discoveries. The Big Bang Theory is the prevailing scientific explanation for the origin and early development of the universe. According to this theory, the universe began as an incredibly hot, dense point about 13.8 billion years ago. This initial singularity contained all the matter and energy that eventually formed galaxies, stars, planets, and everything we observe today. The term Big Bang is somewhat misleading, suggesting an explosion, but it was more of a rapid expansion. From this initial state, space itself began to stretch and expand, cooling and becoming less dense over time. As the universe expanded, it went through several critical phases. In the first fraction of a second, it experienced an unimaginable burst of expansion known as cosmic inflation, which smoothed out the irregularities and initiated the formation of large-scale structures. After inflation, the universe continued to expand and cool, allowing subatomic particles to form and eventually combine to form simple atoms. About 380,000 years after the Big Bang, the universe cooled enough that electrons and protons formed neutral hydrogen atoms, making the universe transparent to radiation. This event, known as recombination, gave rise to the cosmic microwave background radiation, CMB, a faint glow that pervades the universe and provides a snapshot of infant space. Over billions of years, gravity gradually pulled matter together to form stars, galaxies, and eventually clusters of galaxies. Observations of distant galaxies show that these structures are moving away from us, indicating that the universe continues to expand. This constant expansion is driven by dark energy, a mysterious force that accounts for about 70% of the total energy content of the universe. The Big Bang theory is supported by a range of evidence, including CSBMs, the abundance of light elements such as hydrogen and helium, and the observed redshift of galaxies. All of this evidence fits together to form a picture of a universe that has evolved over nearly 14 billion years, from a hot, dense beginning to the vast, complex cosmos we see today. There are several key pieces of evidence that strongly support the Big Bang theory, and each contributes to our understanding of the origin and evolution of the universe. First, one of the most compelling pieces of evidence is the cosmic microwave background radiation. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint glow pervades the entire universe and represents the afterglow of the Big Bang. The CMB is a snapshot of the universe taken about 380,000 years after the Big Bang, when it cooled enough for protons and electrons to combine into neutral hydrogen atoms, making the universe transparent to radiation. Precise measurements of the SDB, especially by instruments such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have provided a detailed map of temperature fluctuations in the early universe that is fully consistent with the predictions of the Big Bang model. Second, the observed abundance of light elements such as hydrogen, helium, and trace amounts of lithium provides further support for the Big Bang theory. This prediction success is attributed to a stage known as Big Bang nuclear fusion, which occurred in the first few minutes of the universe's existence. During this brief period, conditions were hot and dense enough for nuclear reactions to occur, fusing protons and neutrons into light nuclei. The resulting ratio of these light elements is consistent with what we observe in space today, providing strong support for the Big Bang model. Finally, the redshift of distant galaxies, discovered by Edwin Hubble in the 1920s, provides dynamical evidence of an expanding universe. Hubble observed that galaxies are moving away from us in all directions, and their light is stretched to redder wavelengths as they move away. The redshift phenomenon fits perfectly with the idea of a universe that originated in a hot, dense state, and has been expanding ever since. The farther away a galaxy gets, the faster it moves away from us, further supporting the model of continuous cosmic expansion arising from a single source. Together, this evidence forms a consistent and compelling case for the Big Bang theory, weaving a rich tapestry that explains the genesis of the universe and its subsequent evolution. The Big Bang theory explains the creation and early evolution of the universe by stating that everything began with a primitive singularity, very small, hot, and dense, nearly 13.8 billion years ago. This singularity contains all the matter and energy that make up the visible world. This explosion is not an explosion in space, as we thought, but an expansion of space itself. This expansion caused the universe to explode from this point into the vastness of the universe. In the beginning, the universe was hot and dense, with no particles or forces known today. In the first split second, the world experienced a phase of exponential growth known as global inflation. This expansion smoothed out the sharp edges of the past and formed the basis for the large-scale structures we see in the universe today, such as galaxies and galaxy clusters. After accretion, the universe continued to expand and cool, leading to the formation of subatomic particles and simple atoms. When the universe cooled, about 380,000 years after the Big Bang, a major process called thermonuclear fusion occurred. Meanwhile, electrons and protons combined to form neutral hydrogen atoms, and the world glowed with radiation. This process produced the cosmic microwave background radiation, the CMB, essentially the afterglow of the Big Bang, which we can still observe today. The CSBM is a snapshot of the universe at that early time, capturing the conditions that existed when the universe transformed from opaque plasma to transparent space. The first stars and galaxies. Small fluctuations in the density of matter left over from cosmic inflation eventually grew into the large-scale structures we see today. Stars evolved and died, saturating the cosmos with heavier elements formed in their cores, which later formed new generations of stars and planetary systems, including our solar system. The Big Bang theory, supported by abundant evidence such as the cosmic microwave background radiation, the abundance of light elements, and the observed redshift of galaxies, provides a comprehensive framework for understanding the origin, evolution, and large-scale structure of the universe. It presents a coherent narrative that traces the cosmos from an incomprehensibly hot and dense beginning to its current state, and it continues to expand and evolve in ways that we are still trying to fully comprehend. The conditions preceding the Big Bang remain one of the deepest and most enigmatic mysteries of cosmology. According to our current understanding, the singularity from which the Big Bang emerged contradicts traditional physics. This singular point is believed to have been infinitesimal and infinitely dense, compressing all the matter and energy that eventually made up our universe. In this extreme state, the known laws of physics, including general relativity and quantum mechanics, break down. Thus, the question of conditions before the Big Bang can be problematic, since time itself, like space, came into existence as a result of the Big Bang, making the concept of before somewhat meaningless in classical terms. One speculative idea is that our universe may not be an isolated event, but part of a larger and more complex multiverse. Multiverse theory suggests that our universe may be just one of many universes, each with its own physical laws and constants. Some models propose a cyclic universe in which each Big Bang is followed by a period of expansion, final contraction, and subsequent big crisis, which then causes another Big Bang. This cyclical model implies a series of endless cycles, denying the need for a beginning or an end. Another intriguing area of research is theories of quantum gravity, such as loop quantum gravity, which seek to unify general relativity and quantum mechanics. Some of these theories suggest that the singularity at the beginning of the Big Bang may have been replaced by a quantum jump, suggesting that a previous phase of compression of the universe led to the Big Bang and our current phase of expansion. Although these ideas are purely theoretical and lack empirical evidence, they offer fascinating insights into possible pre-Big Bang scenarios and the nature of space-time at the most fundamental level. In short, while the conditions preceding the Big Bang remain speculative and shrouded in mystery, continuing advances in theoretical physics and cosmology may eventually yield a deeper understanding. These works continue to challenge our understanding of time, space, and the very structure of the universe. Scientists study the early moments of the Big Bang using astronomical observations, particle physics experiments, and sophisticated computer modeling. One of the most important tools in this work is the cosmic microwave background radiation, the faint afterglow of the Big Bang. By observing and analyzing CSBMs, scientists can gain information about the state of the universe when it was only about 380,000 years old, a fraction of its current age. Instruments such as the Wilkinson Microwave Anisotropy Probe, WWMAP, and the Planck satellite have mapped tiny temperature fluctuations in the CMB with extraordinary precision, providing insight into the initial conditions of the universe. We continue to study its rate of expansion and the distribution of matter and energy. Particle physics also plays an important role in studying the early universe. Facilities such as the Large Hadron Collider at CERN recreate the extreme conditions that existed a fraction of a second after the Big Bang, pitting particles against each other at incredibly high energies. These experiments allow scientists to investigate the fundamental forces in particles that governed the early universe, test theoretical models, and look for phenomena such as the Higgs boson, which helps explain how particles acquire mass. Thus, particle physics discoveries can provide indirect evidence of the state of the universe at its earliest moments, and confirm the predictions of cosmological models. In addition, computer simulations and models play an important role in understanding the early universe. By inputting observational data and physical laws into supercomputers, scientists can simulate the evolution of the universe from the Big Bang onward. These simulations allow us to test hypotheses about processes such as cosmic inflation, the rapid expansion of the universe during its earliest moments, nucleosynthesis, the formation of light elements, and the formation of large-scale structures such as galaxies and galaxy clusters. But by comparing the results of these simulations with real astronomical observations, scientists can refine their theories and better understand the complex dynamics that shaped the early universe. Together, these approaches, observing relic radiation from the Big Bang, recreating high-energy environments in particle gas pedals, and detailed modeling, allow scientists to piece together the complex puzzle of the universe's earliest moments. Through this multifaceted approach, scientists continue to uncover the fundamental processes that laid the foundation for everything we observe in the cosmos today. Cosmic inflation is a theoretical framework that describes the rapid -36 to 10 to the power of -32 seconds after the initial singularity, stretching the universe at least 10 to the power of -26 times in a minuscule fraction of a second. This dramatic growth spurt smoothed out all the initial irregularities, setting the stage for the relatively homogeneous and isotropic universe we observe today. The concept of cosmic inflation was first proposed by physicist Alan Guth in 1980 to address several fundamental problems with the standard Big Bang theory. One of these is the horizon problem, which asks why distant regions of the universe appear to be so similar in temperature and density, despite seemingly not having had enough time to exchange information or energy. Inflation addresses this problem by suggesting that these regions were once much closer together and then rapidly moved apart, allowing them to equilibrate in temperature and other properties. Another problem that inflation raises is the flatness problem, which concerns why the universe appears spatially flat rather than curved. For the universe to appear flat today, the parameters of its early density had to be established with remarkable precision. Cosmic inflation helps explain this fine-tuning by suggesting that the original curvature of the universe has been drastically reduced by rapid expansion, making the observable universe appear flat on large scales. In addition, cosmic inflation provides a mechanism for the emergence of the large-scale structures we see today, such as galaxies and galaxy clusters. Quantum fluctuations in the inflating universe were stretched to macroscopic scales, and subsequently became the seeds of these cosmic structures. These primordial fluctuations are captured in the cosmic microwave background in the form of small temperature variations that we can observe today. This prediction has been convincingly confirmed by data from instruments such as the Planck satellite, which has recorded these tiny variations with remarkable accuracy. Cosmic inflation offers a compelling explanation for the homogeneity, isotropy, and flatness of the universe, and explains the initial rudiments of structure observed in the cosmic microwave background. It has become a cornerstone of modern cosmology, providing a critical understanding of the nature of the earliest moments of the universe. Accelerometer theory explains the expansion rate of the universe by accounting for the presence of a horizontal electric field called the accelerometer field. This field created a period of global growth from subatomic scales to macroscopic dimensions in a fraction of a second. The inflaton field has unique properties. Other forms of energy are stronger and create a gravitational effect that causes space to expand at a greater rate. This expansion was so rapid and so significant that in less than a second, the universe grew 10 times to the 26th degree, to 1, and then to 26 times 0. During this period, the energy density of the plateau remained relatively constant and maintained exponential growth throughout the area. This is in stark contrast to the conditions of the universe after inflation, when expansion was slow and the density of matter and radiation was low. Eventually, the inflaton field decays into particles and radiation, heating the universe to a hot and dense state that marks the aftermath of the Big Bang. This transition from the expansion phase to the Big Bang phase is known as cooling. The rapid economic growth caused by inflation had many profound effects on the structure and dynamics of the world. First, it smoothed out any initial inhomogeneities and irregularities, resulting in the remarkably homogeneous and isotropic universe we observe today. This mechanism elegantly solves the horizon problem, which raises the question of why distant regions of the universe have essentially the same properties, despite being causally unrelated to each other. Second, inflation explains the flatness problem by eroding any initial curvature the universe may have possessed. Exponential expansion stretches the fabric of space to the point where the observed universe appears flat, which is consistent with observational data that shows that the geometry of the universe is very close to flat. In addition, inflationary theory explains the origin of the large-scale structure of the universe. Quantum fluctuations in the inflaton field during inflation increased to cosmic scales, generating density variations that later evolved into galaxies, clusters, and huge cosmic structures. These fluctuations are captured in the cosmic microwave background in the form of tiny temperature variations that have been mapped in detail by instruments such as the Planck satellite. Inflationary theory provides a consistent and elegant framework for understanding the rapid expansion of the universe. The positing of the inflaton field and its unique properties explains how the universe went from an incredibly tiny, dense state to the vast, smooth, and structured cosmos we observe today. The theory of cosmic inflation is supported by several strong evidences that are consistent with observations and predictions of the early universe. One of the most important pieces of evidence is the microwave background radiation, the heat left over from the Big Bang. Another important piece of evidence is the great creation of the universe. The distribution of galaxies and galaxy clusters is not random, but reflects the structure of a planetary network with strings and giant holes. This transition can be traced back to previous differences in density, amplified by inflation. Accurate computer simulations based on inflation models can reproduce these large-scale structures, similar to what astronomers see with telescopes and space probes. Evidence that enhancement has been successfully achieved is also the smoothing problem and the weather problem. Observations show that the geometry of the universe is close to flat. According to Einstein's general theory of relativity, the flat universe was completely independent and perfect at the beginning of its history. Increase explains this flat appearance by the rapid expansion of the initial curvature, which makes the universe appear flat even in its initial state. In addition, the isotropy of relic radiation, its uniform temperature in all directions, poses a problem known as the horizon problem. Regions of the universe separated by vast distances have the same temperature, even if they are not causally related to each other. Inflation solves this problem by suggesting that these regions were once in close contact, and then pushed apart by rapid expansion, allowing them to reach thermal equilibrium. Furthermore, the recent discovery of primordial gravitational waves, if confirmed, would provide direct evidence for inflation. Gravitational waves are ripples in spacetime that originated during inflation and leave a characteristic imprint known as B-mode polarization in the CMB. Although initial claims of such a discovery made by the BICEP-2 collaboration in 2014 were later attributed to interstellar dust, the search continues, and their confirmation would be a strong endorsement of inflationary theory. Together, these lines of evidence, CBM anisotropy, large-scale structure, flat structure, and the horizon solution, provide a robust justification for cosmic inflation. Each line of evidence is consistent with the predictions of inflationary theory, reinforcing it as a cornerstone of modern cosmology. Cosmic inflation has significantly altered our understanding of the edge of the universe, essentially reversing the concept of cosmic boundaries. Prior to inflationary theory, questions about the boundaries of the universe often revolved around whether the universe was finite or infinite, and what might lie beyond its observable limits. Inflation provides a framework that both resolves these questions and complicates them, greatly expanding the scope of what we think of as the universe. During the inflationary period, the universe expanded exponentially, stretching space-time so much that regions that were originally close together were pushed far beyond the observational horizon. This rapid expansion means that any pre-existing irregularities or initial boundaries have flattened out, creating a homogeneous, isotropic universe on large scales. As a result, the concept of edge is becoming more abstract. The edge is best understood not as a physical boundary, but as the limit of our observational capabilities, the observable universe. Inflation makes the observable universe only a tiny part of the entire cosmos, which may be much larger or even infinite. Inflation also suggests that other regions with different physical conditions or constants may exist beyond our observable universe. This idea is often embodied in the multiverse theory, where our universe is just one bubble in a frothy sea of multiple, possibly infinite universes. Each of these bubbles may have gone through its own inflationary period, resulting in very different properties and laws of physics. This perspective of the multiverse fundamentally changes our conception of the edge of the universe, transforming it from a geometric boundary to a boundary of observational reach, beyond which lie potentially infinite and diverse realms. Inflation also affects our understanding of what may lie beyond the limits of our observational capabilities. Because inflation expands space so rapidly, regions that are now many billions of light-years apart were once in close contact. This suggests that regions outside our observable universe may be very similar to what we see within it, being part of a single, interconnected entity much larger than what we can currently observe. However, if the universe is infinite, then these regions extend to infinity, further complicating the concept of an edge. Inflationary theory redefines the boundary of the universe, extending our view of the cosmos far beyond observable limits. It moves the boundary from the potential physical end to the observational horizon, opening up the possibility of a much larger, possibly infinite universe. This broader structure opens new questions and deepens our understanding of the complex, dynamic, and ever-expanding fabric of space-time. Cosmic inflation is the mind-boggling concept that the universe underwent exponential expansion in an incredibly short period of time, just a fraction of a second after the Big Bang. Potentially, this rapid inflation could extend far beyond our observable universe, creating the tantalizing possibility that it could have given rise to multiple universes, often referred to as a multiverse. In this diverse cosmic ensemble, each universe may possess its own set of physical laws and constants, wildly different from the reality we are accustomed to. Imagine a reality where gravity is noticeably stronger, or where stars burn a different color. The possibilities are as fascinating as they are limitless. At the heart of this idea is the assumption that inflation was not a one-time event, but rather a continuous process that may be generating new universes even now. In this case, regions of space that are inflating at different rates separate and become separate universes, each encased in its own bubble. The scientific justification for the hypothesis relies on quantum field theory and general relativity theory, although it is worth noting that the multiverse hypothesis remains speculative as there is currently no direct observational evidence. Even so, the concept begs the question of the limits of what we perceive as reality and provokes endless questions about our place in a potentially infinite and diverse cosmos. What if, in another universe, someone like you is pondering the same cosmic mysteries, but under stars that shine in colors we've never seen before?